So we're going to do some practice involving problems where we find and classify using the second partials test. Now, we've already talked about the second partials test for functions of two variables. I do want to mention, you can do the second partials test for functions of any number of variables. It just gets a little bit more interesting. And in particular, you need to have a little bit more linear algebra background to really appreciate the subtleties that can happen. So we're only going to focus on functions of two variables. Woohoo! And if anything, the big theme from today is two equations and two unknowns. And that's the hard part. And once you figure out how to handle that, life is not so bad. But how do you do it? Well, the answer is practice. The more you practice, the more comfortable you get by saying, oh, I can do things. I can solve. I can factor. I can substitute. And so make sure you do as much practice as you can. If you're following along with the video, make use of the pause button. See a problem that you like, pause it, and then try it yourself. And they might say, how do I know I'm going to like this problem? Well, I think you'll like all math problems, right? Because isn't that the case that all math problems are fun? I hope so. Well, let's begin. Our first problem, for the function g of xy, which is x minus y squared times sine of x, show that 0, 1 is a critical point and classify the critical point. So here we don't have to find it. They handed it to us on a nice platter. It's like, look, here it is. All right, well, let's take a look. Now, when we talk about critical points, and especially when we talk about classifying, what we really say is, look, that's the place where the gradient has to be 0. Now you might say, well, wait a second. I thought the gradient could be undefined. Well, yes, that is a critical point. But when we talk about classifying, the only place that we have a way to do local classification is when the gradient is 0. So, well, let's take a look. G sub x is, taking derivative with respect to x, 1 minus y squared cosine of x. And g sub y, well, that goes away, minus 2y sine of x. So the gradient of g, 0, 1, is, well, 1 minus 1 squared cosine of 0, comma, minus 2 times 1 times sine of 0, which is, well, since cosine of 0 is 0, cosine of 0 is 1, and sine of 0 is 0, you get 1 minus 1 and 0, also known as 0, 0, which is just the 0 vector. See, this is not the 0 number. We'll make it clear that it's a vector. We'll put a little arrow on top. Aha, now no one will doubt it's a vector. Okay, so that's the first part. We said show that this is a critical point. And that's the verification. We've now shown it's a critical point because we saw, aha, the gradient is 0. Now the classify. So the classify, same process that you do for all these problems. You're going to look at this expression, gxx, gyy minus gxy squared. That's what gives the sort of information, storing our information. All right, so let's go through and fill these pieces in. Well, we should probably take our derivatives here for reference. Gxx. Okay, first part goes away. Derivative of cosine would be minus sine. Okay, so we end up with y squared sine of x. Gxy, well, minus 2y cosine of x. And gyy would be minus 2 sine of x. All right, so we plug it in at the point 0, 1. So we plug in x equals 0, y equals 1. Gxx will be 0, because we have sine of 0 is 0. Gyy, sine of 0 is 0. Okay, 0 minus gxy. Well, that's 2 times 1 times cosine of 0 is, well, 2. Don't forget the minus. And so it's minus 2 squared. Now, sometimes people might make a little mistake here. If you have a minus 2 squared, square the minus as well. So it's really 4. Coming out of the square, then there's a minus sign, so you get minus 4. Well, that's negative. And when this quantity is less than 0, what it means is in one direction, you feel like you should be a max, and in a different direction, you feel like you should be a min, which means that our point, this is a saddle point. Neither max or min. And there we go. Done. Well, of course, we knew the critical point ahead of time. So that was oftentimes the hard part about these problems, is where is the critical point? Once you know, it's not so bad. Well, let's do another problem. Find and classify the critical points of the function x squared minus 3xy plus 2y squared plus x minus y. Okay. Now, I will say there's a common theme here. When we see the word classify, pretty much that's always going to be a second partials test. I can't think of a problem that we've seen the word classify anywhere else. So that's why I'm using pretty much just to hedge my bets. But when you see classify, we're in second partials. The process is always going to be the same. Set the gradient equal to 0, which means your partial derivative is equal to 0. Find your points, and then use their second partials test. So you have to look at that expression, fxx, fyy minus fxy quantity squared, and interpret. So we're going to have a lot of the same sort of pattern today. And it's going to feel very repetitive. But what we're really going to be practicing, the big thing for today, is practicing solving 2 equations and 2 unknowns. Once we're comfortable with that, life is good. So let's begin. So we're going to start by finding. You have to find before you classify. You can't classify a point if you don't know where the point is. So fx equals and fy equals. So fx, 2x minus 3y plus 1 equals 0. Fy minus 3x plus 4y minus 1 equals 0. So we can rewrite this. 2x minus 3y equals 1 minus 3x plus 4y equals 1. Oh, that should have been a minus 1 when I bring it across. There we go. All right. 2 equations, 2 unknowns. And these are the nice kinds of equations and unknowns, which is good. Let's warm up with something we're comfortable with. Now here, when it's, we would call this a linear, and the phrase linear basically says, look, everything's to the first power. So x to the 1, y to the 1. There's no x to high power. There's no x times y. These are our nice ones. So one thing we can do is we can do substitution, we can do solve, we can do combining. And I like to do combining when I have linear equations. So for instance, let's suppose we wanted to cancel out the y's. Well, I have minus 3y, and there's 4y. I say, okay, 3 and 4, let's try to get things up to 12, because the least common multiple is a fancy way of saying, what's the smallest number that both 3 and 4 divide? So if I multiply this by 4, multiply this by 3, what will happen? Well, we'll get 8x and minus 9x, that's minus x. But the important thing is minus 12y plus 12y, gone. See, that's why we chose those numbers, to get cancellation. Minus 4 plus 3, minus 1. So say, aha, x has to be 1. Once you know x, you can solve for y. Now you could also do another combination. Well, either way works. So 2 minus 3y equals minus 1. So this is plugging x equals 1 into the first equation. And we do a little bit of swapping around. 3y equals 3, and y equals 1. Okay, so we get y equals 1, x equals 1, which really means we have one critical point, and it's at the point 1, 1. I want to pause for a second here. We've done everything right. This is not I'm going to criticize what we've done. Sometimes it doesn't matter if we add more points. Sometimes it does. And so I want to be very emphatical here. When we talk about finding and classifying critical points, don't find extra critical points. In other words, you say, oh, well, maybe I should throw in some other points just for fun. Or I make some strange algebra assumptions. No. Don't do that. Don't do that. Be careful. The thing is, classifying, in other words, using the second partials test, is completely uninformative if we don't know what's happening with the first derivatives. In other words, you have to be at a critical point in order for the classification to make sense. So make sure you don't rush through finding the points, because if you find the wrong points, forget it. Game over. Game over. All right. So back in. Now, the next step is to do our classification. So we're going to look at this quantity D, which is fxx times fyy minus fxy quantity squared. Well, all right, so let's take a look at these derivatives. All right, so we have fxx, that's easy, 2. fyy, 4. And then fxy, okay, take the derivative of y. When we already took the derivative with respect to x, will give us negative 3. Or taking the derivative with respect to x, when we already took the derivative with respect to y, also negative 3. They'll be the same when we have nice functions. Then we're going to be doing a lot of nice functions today. So what do we get? We get 2 times 4. All right, that's 8 minus negative 3 squared, 9. That's definitely negative. That's a negative number. So our conclusion is that 1, 1 is a saddle. So when we have this quantity coming out, and it's a negative quantity, that means the point that we found is a saddle point. All right, well, great. Progress. Good. Well, keep going, right? Because, we got to keep working our way up. The more challenging the problems, the further up we go. We want to get to the top, climb the, Mount Calculus and summit. All right, so our next problem. Find all the values for k so that f of xy, which is x squared plus kxy plus y squared, has a local minimum at 0, 0. And give your answer in the form of an interval. All right, well, good. This should be interesting. Let's see where we go. Now, we want to say, okay, we need to have our critical point be at 0, 0, because it's a local minimum, which means it needs to be it needs to be critical, right? Because a minimum has to occur at a critical point. Okay, so, but notice, no big surprise. If we look at fx, that's 2x plus k times y. And if you look at fy, that would be kx plus 2y. And so, if you plug in x equals 0, y equals 0, everything becomes 0. So at the point 0, 0, we have that the gradient of f is the 0. And I'll put a little arrow just to emphasize 0 vector, not 0 number. Okay, so we always know that 0, 0 is a critical point, but it says, look, it needs to be a local minimum. Okay, so let's push a little bit further. What do we have? Well, we look at this expression d, which is fxx fyy minus fxy squared. Now, what are these things? Well, we can actually compute this. fxx is 2, fyy is 2, and fxy would be k. And so, k squared. So we say, okay, great. This is 4 minus k squared. All right. Now, where do we go from here? Well, what do we need? in order to be a minimum, what has to be true? Well, let's recall what's true about D. So if D is negative, that says it's a saddle. If D is positive, well, then you look at fxx, and if that's positive, then you have a min. And if fxx is negative, you have a max. And if D equals 0, well, more work. Really, it's inconclusive. So we say, okay, look, what needs to be true? What needs to be true is when we look at our D, it has to be positive. Now, notice something. This is nice. We really want to key off of fxx. But notice that our fxx, it's 2. So f of fxx is always positive. So we say, aha, perfect. So what we really want is we want this to be positive. Because if that's positive, our fxx is also positive, we're at a local min. Ha ha, perfect. Okay, now, what happens? Well, all right, what does this become? This becomes, we want k squared less than 4, or absolute value of k, which is what you get when you take the square root of k squared, is absolute value of k, is less than 2. Or put another way, you can say, aha, negative 2 less than k less than positive 2. Okay, so definitely in this range, we're out of a local min, for sure. I'm not saying this is our answer yet, but I'm saying these points have to be included. Now, we can also rule things out. We can say, hey, if this value of D is ever negative, it's got to be a saddle. So if 4 minus k squared is negative, or another way to put that, k squared is greater than 4, or the absolute value of k is greater than 2, or we could say k is below negative 2, or k is above positive 2, then it's a saddle. And now you're like, perfect. We're done, right? Ah, wait, hold on. Not quite, right? There's 2 points left. So we got to think about those 2 points. So what are the 2 points that are left? So now the question becomes, well, okay, we know if we're sketching our line, so to make it here, we have these points, negative 2, positive 2. These points are out. Those would be saddles. The points in between are in. Those would be mins. The question is, what happens at those endpoints, at those transitions? Well, let's think a little bit. So let's try to see what happens with the function. If we plug in k equals, we'll start with 2. Let's be positive. We're optimists, right? We're always looking at the bright side of life. We always should look at the bright side of life. Okay, x squared plus 2xy plus y squared. The thing is, at this point, the second partials test doesn't work. Because we're going to get d equals 0. Inconclusive, which really means more work. So now we're doing the more work. What does the more work mean? Well, more work says, can we figure out another way to think about it? Well, let's look at our function. X squared plus 2xy plus y squared. What's another way to think about that? Well, it's a perfect square. This is x plus y squared. Now, what do we know about x plus y squared? Well, one thing we can say for sure, absolutely positive, is that this is always greater than or equal to 0. Always, always, always. Because if you square something, it's going to be greater than or equal to 0. And we know that f of 0, 0 is 0. So what does that say? It says that at the origin, or 0, 0, we have a value of 0. and nothing is below that. Okay, well that means that we're a local minimum. Now here's where it gets interesting, because think about what the graph looks like. What you have is that if you look at the function x plus y squared, it looks like a trough. So it's like you took your piece of paper and folded it up, made it in a U shape. So if I sit along that line, x plus y equals 0, everywhere along that line I actually have a value of 0 in the function. But remember, minimum does not say I have to be strictly less than all the points nearby. I can be less than or equal. So, conclusion, we get to include that endpoint. What about negative 2? Well, I bet you can see where we're going to go here. So, all right, we've got x squared minus 2xy plus y squared, which is, again, a perfect square greater than or equal to 0. And we still have that at 0, 0, we're equal to 0. So that means, look, 0 is as low as we can get. And so at the origin, we're as low as we possibly can be, and therefore it is the case that 0, 0 is still a minimum. So we will include the endpoints. So our final answer, because remember, we had to find all of them, not just most of them, all of them. So our final answer in the form of an interval is negative 2 to positive 2, and we include the endpoints. And that's it. What a good problem. What a nice, good, fun problem. Wow. Good times. All right. Well, let's keep going. Do more problems. The more we do, the better we get. Let h of xy equal x squared minus 6x cosine y. X is arbitrary, and y goes between negative pi to pi, strictly between. Find and classify all the critical points. Now, one of the reasons we're doing this is sometimes when you do a lot of find and classify problems, you get to the point where it's like, oh, everything's just polynomial. The thing is that the reason you see so many polynomial problems in find and classify is because those are the ones where we can actually succeed in finding. At least in some cases we can. But the theory says, look, it doesn't have to be a polynomial function in order to talk about things. And so this is an example that says, hey, there are some non-polynomial functions where we can still make progress. So let's make progress. How do we begin? Well, we always start with the find. You can't jump to the classify. You have to start with the find. So we look at our partial derivatives. H sub x. Well, okay, that's not too bad. 2x minus 6 cosine y. And we're going to set that equal to 0. Of course, I say that doesn't look so bad, but now that I look at it, it's like, I don't know, that's kind of looking not great. Well, keep going though, right? Keep going. Let's look at hy. Maybe that'll be more hopeful. Let's see. 0. That's already looking hopeful. And the minus 6x is like a constant. Derivative of cosine is negative sine. So we end up with 6x sine of y. And we set that equal to 0. Now, between the two, the h sub y is looking really nice. And the reason it looks really nice is we have stuff multiplying together equals 0. Well, that's perfect. We love stuff multiplying together equals 0. It's our favorite thing. Because when we have that happening, in other words, when stuff multiplies together and the output is 0, that says something. What it tells us is that one of the pieces has to be 0. So there's really two possibilities. One thing is that the x could equal 0, and another is that sine of y could equal 0. All right, so now we have to start thinking about what does this mean. Well, let's start with the x equals 0. If I know that x equals 0, and that's based on h sub y, I need to figure out what's true about y. So I go into h sub x, substituting in x equals 0. That would imply minus 6 cosine of y has to equal 0, which really means that cosine of y has to be 0. All right, well, now we have to think about the cosine function. Well, it equals 0, we cosine at right angle, pi over 2. But there's other places, and we want to make sure we capture them all. And in particular, everything between negative pi and positive pi. So that leaves to two possibilities, namely pi over 2 and the negative of pi over 2. Everything else, there are infinitely many times when cosine equals 0, but not when we're also between negative pi and pi. So when we put that together, that's going to lead us to two critical points, 0 and pi over 2, comma, 0 and negative pi over 2. All right. So that was down one of our tracks. Now we've got to go down the other one. Sine of y equals 0. Again, we're talking about y between negative pi and positive pi, so when does sine equal 0? At 0. The next time that sine equals 0 would be if you went to pi, but by pi we're out. Or if we went to negative pi, but again, we're out. So that says, okay, look, this is really y equals 0. Now, take that information, plug it in to our h sub x. That tells us 2x minus 6 cosine of 0. Oh, wait, cosine of 0 is 1. So 2x minus 6 equals 0. All right, well, that says what? X equals 3. So we get to the point 3, 0. All right, so we have 1, 2, 3. 3 critical points. Good. And it's okay to have many critical points. You might have one, might have many. It's even possible to have none. It just depends on the function. But now we're done with the find stage. We transition now to the classify. All right, so for classifying, well, we're going to need our second derivatives. So let's find them. hxx. Well, that's pretty easy. 2. hyy. That's also not too bad. That'd be 6x cosine y. And hxy, which is the same as hyx, you can do either one. In fact, if you look at hyx, probably even easier, right? Taking the derivative with respect to x, so 6x sine y leaves you with 6 sine of y. All right, so we look at our value for d. I think it stands for discriminant, but well, whatever it stands for, here we go. 2 times 6x cosine y minus 6 sine of y squared. All right. Now we just go through and patiently see what happens for each of these values. So let's plug in our 0 pi over 2. If we do that, what happens? Well, we're going to get 2. 6 times 0 times cosine of pi over 2, which is also 0. All right, 2 times 0 minus sine of pi over 2 is 6. So, and then we have sine of pi over 2 is 1 times 6 is 6. Square it, 36. Well, negative 36, that's less than 0. Great. So that means that this point, 0 pi over 2, this is a saddle. All right, great. If we do the same thing with negative pi over 2, we're going to run into the same things, right? We still have 2, and we still have a 0. Cosine negative pi halves is still 0, so 0. And here, sine of negative pi halves is negative 1. So we get negative 6 on the inside, but you square, it's still going to end up being subtracting 36. We're still negative for this d, which means that this point is also a saddle point. All right. One more to go. Plugging in 3, 0. Well, we're going to get 2. Then we have 6 times 3 times cosine 0. Well, that's 6 times 3 times 1. That's 18. All right, minus, now sine of 0 is 0. So times it by 6, still 0. Square of 0 is still 0. So we end up with positive 36, which is positive. Now, at this point, what can we conclude? We can conclude that 3, 0 is a local something. But local what? Okay, this is the part where the second partial test is slightly different than the second derivative test. We can't just say, aha, positive, all right, ah. No. We're going to say, okay, now we dig a little deeper. We key off of the second derivative, either with respect to x or the second derivative with respect to y. So we look at these and we say, okay, what's true about them? So in particular, we can see them both here, right? They're 2 and they're 18. They're both positive. So thinking back to the second derivative test for single variable calculus, when we see things are positive, that means that we're looking like a smiley face. We look like a min. And that's really what's captured, right? We're saying what's happening in our slice when we look at our second derivative with respect to x, or we look at our second derivative with respect to y. So we are a local min. And we're done. That's it, right? Because we said, look, we found and classified all the critical points. There we go. Good. Great. That's not so bad. We can do more of these. That's wonderful because we have more of these to do. All right. So let's do our next problem. Find and classify all the critical points of the function x cubed plus y cubed plus 2x squared minus 3y squared minus 8. Okay, wow. What a function. Well, don't worry. We'll have even more fun functions later on. In some sense, this function perhaps is not the most appealing on the surface because there's not a lot of really interplay going on between x and y. You see, like there's stuff with x and there's stuff with y, but they really don't mesh together. And so it shouldn't be too bad. It's when they start kind of like coming together. That's when we have fun. Oh yeah, that's when we'll have a lot of fun. So our process is the same. Start by taking our partial derivatives. So fx, 3x squared, and then here plus 4x, and we're going to set that equal to 0. All right, and f sub y, well, 3y squared minus 6y, and again, set that equal to 0. And all right, we got to just work through the process. We're patient people. No need to rush. So for the first case, well, let's factor out in x. So you can say x times 3x plus 4 equals 0. Well, that leads us to the conclusion x equals 0 or x equals minus 4/3. And similar, in the second equation, we factor out 3y. So 3y times y minus 2 equals 0. Well, that gets us to y equals 0 or y equals 2. All right, great. Well, now what comes next? Well, what comes next is we look at the following. We say, what are our points, right? Because we have, okay, in the first equation we had these two possibilities, in the second equation we had these two possibilities. And the answer is, well, we take all combinations. So we actually have 4 critical points. So they'd be at 0, 0, right? 0, 0, 0, 2, negative 4/3, 0, and negative 4/3, 2. All right, good. Now, those are our critical points. So we've finished our find. We're ready to start our classify. Well, time to transition, so we'll change colors, right? Good, great idea, I like that. So we should start by looking at our second derivatives. So what are our second derivatives? fxx, that would be 6x plus 4. And fyy, that would be 6y minus 6. And fxy is 0, like we said before. Look, this function, the x and y really aren't meshing together very well. All right, well, let's figure out what's happening here. So when we look at our expression for D, that's our fxx, fyy minus fxy squared. Well, what we really get is 6x plus 4 and 6y minus 6, and then there's nothing there. All right, so point by point, let's go through it. So when we plug in 0, 0, what do we have? Well, 4 times negative 6. And that's a negative value. And therefore, we say, aha, when we see a negative, 0, 0 is a saddle. So negative value means a saddle point. All right, how about 0, 2? What's happening there? Well, we're going to get 4, and here we're going to get 12 minus 6, which is plus 6. So we're going to get 4 times positive 6. Well, that's positive. Now we go a little bit deeper. Okay, now we look at fxx or fyy, and it doesn't matter which one we pick. If we plug in 0 into fxx, we get 4. If we plug in the 4, really we're plugging in the whole point, but in our case, there's only one variable in each one. What we see is our second partial derivatives are both positive. Great. Well, that means that this point, 0, 2, that's a local min. All right. Well, how about this other point, negative 4/3, 0? What happens there? So, well, let's work it through. Negative 4/3 times 6 is negative 8, plus 4 makes a negative 4. And then, of course, 0 minus 6 is minus 6. Well, negative 4 times negative 6, that's positive 24. But we don't care about the 24-ness. We care about the positiveness. So the fact that it's positive, great. Now we have to go deeper. In our case, go deeper means what? Well, it means look at those fxx or fyy terms. We see that they're negative values. So that tells us that we're at our local max. And our last point, negative 4/3, 2. Well, okay, so we're going to get negative 4 in the first slot. In the second slot, we'll get positive 6, which is negative. All right. Well, if it's negative, that means that we are at a saddle. Now, in some sense, it's kind of a fun function because we're like, ooh, we had a min and a max in the same one. A lot of the very simple functions tend not to do that. But in another sense, because there wasn't any interplane between x and y, in other words, there's no term that involved both x and y multiplied together, what's really being captured here is what's the behavior for the functions. If you think about, say, in terms of just the x part, the x cubed plus the 2x squared, what's going on? Well, in the x cubed plus the 2x squared, if you were to plot the function, what you would discover is negative 4/3, it's a minimum, it's a maximum, and 0 is a minimum. So it's like, okay, so in terms of just the function x cubed plus 2x squared, we have this is a min and this is a max. And in a similar way, if you run it through for y cubed minus 3y squared, what you'll discover is that y equals 2 is a min. And you can't even read that. It's supposed to say min. And at y equals 0, it's actually a max. And so it's not too surprising that when we have the max with the part that involves x and with the part that involves y, it is a max. And when we have a max in the part that involves, when we have a min in the part that involves x and a min in the part that involves y, it is a min. So it's like, aha. And when it's a min in one part and a max in another part, then it's neither. And it's like, well, okay, well, that kind of makes sense. But we want things to be more interesting. Let's mesh or perhaps smoosh. We want to get the x's and y's together. We want to have a chance to, do some algebraic flexing, like, look at our algebra, look at us. So let's do another one. Let's see if we can't get some algebra going here. So our next problem. See, look, I can already see x's and y's multiplying together. Great. So find and classify the critical points for this function, x squared y plus x squared minus 6xy plus y squared minus 6x plus 7y. All right. Oh, nice. Good. So what do we do? Well, okay, let's proceed. It's the same process, right? Partial derivatives, set equal to 0. That's our find. Then we go into our classify stage. So, f sub x, 2xy plus 2x minus 6y minus 6 equals 0. And our first reaction when we see that is like, But we say, look, we also get to do f sub y, right? Okay, let's do that. Okay, f sub y is x squared minus 6x plus 2y plus 7. I set that equal to 0. Okay, great. Well, it looks like we're going to have a lot of fun ahead. Now, there's a couple of different things we can try. One thing we can do, notice the f sub y. What do we see there? Well, there's just a single y. That means that what we can do is we can actually solve for y. So we can solve for y in terms of x. So one possibility is perhaps, and I'm not committing ourselves yet, perhaps substitution. Maybe. Now, I think that would work. But just because it would work doesn't mean that we have to do it. There could be something else we could do. Let's look at our f sub x. This is, something here makes me go, Because oftentimes when we have a problem like this, these aren't randomly chosen functions. They've been carefully crafted by the great calculus crafts people coming together and saying, we're going to form this beautiful problem. So let's think about what they could have done to make a beautiful problem. Now, substitution is great, and I strongly encourage it, but better than substitution is factoring. Factoring is always your can I factor, and if I can, yes. All right. Now, you might look at the partial with respect to x and say, factoring, forget it. But let's not be so hasty. Let's just try it. Now, how can you factor? Well, one way that you can factor is you can say, well, can I put things into some simple groups? Well, here's some simple groups, just the first two, last two. All right. 2x. Now why? Well, notice that they have something in common. So this is sort of factoring by clustering. And what you do is you cluster things that say, oh, these seem to have common terms, so let's pull common things out. So the first two had 2x in common, last two had 6 in common. So 2x, y plus 1, here, followed by minus 6, y plus 1. And then we're like, whoa. Those beautiful calculus people, they did it! They did it! Look at it! Oh, magnifique! Right? Because look, they both have y plus 1 in common. This is great. All right, so 2x minus 6 times y plus 1 equals 0. Ah, beautiful. That tells us there are two possibilities. Because remember, the great thing about factoring, if you have factoring equals 0, something had to be 0. 0 is such a cool number that way. It's the only number, by the way, with this property. only 1. That's why 0 should never be left out of the party. 0 is wonderful. So we get the two possibilities, x equals 3, or, and I really want to emphasize the word or, y equals minus 1. Because I'm not claiming that both the case that x equals 3 and simultaneously that y equals negative 1. I'm just saying at least one of the two should be true. And when we talk about the word or in math, we really mean what's the fancy way of saying this, inclusive or. One, the other. It's possible maybe both, but usually not likely. So we say, okay, now that's from our f sub x. So time for us to sort of take two different tracks down and say what happens if we go and see what that says about f sub y. So let's go down the x equals 3 track. So I'm going to plug in x equals 3 into here. Let's see what happens. We're going to get 9 minus 18 plus 2y plus 7 equals 0. Okay, well, that's looking pretty promising, actually. I think we could probably solve for y, right? Because look, what's happening here? Well, what ends up happening is you say, well, 9 minus 18 plus 7 is negative 2. Bring it across, 2y equals 2, or y equals 1. And remember, we're in the case where x equals 3. So when we combine that, we get the point 3 comma 1. So that's a critical point. Okay, so now we've gone down the x equals 3 track. Time for us to go down the y equals negative 1 track. So what happens on that track? Well, plug in y equals negative 1. We're going to get x squared minus 6x minus 2 plus 7. Because y equals negative 1. So minus 2 plus 7 would make it plus 5 equals 0. Now I think, wow, could it factor? If it could, there's only one possible way. Because 5, the only way to write 5 is 1 times 5. So it'd be x1 and x and 5. They have to be the same sign, and this needs to be a minus in the middle. So that would say, if it factored, it would have to factor as x minus 1 times x minus 5. Okay, well, let's check. X squared minus 5x minus x, that's minus 6x plus 5. Yep, worked out. So we say, okay, that says x equals 1, or of course, x equals 5. But we can combine this with the fact that we know y equals negative 1. So we get 2 more points. 1 comma negative 1, and 5 comma negative 1. So there are 3 critical points. 3. Beautiful. Okay, we've finished the find. And after we do the find, we transition now into the classify. So here we go. We're going to look at our second order derivatives, f(x)(x). All right, that would be 2y plus 2. Fyy would be 2. Oh, that's nice. Okay, how about fxy? Okay, that would be, taking derivative with respect to y here, 2x, and derivative with respect to y, minus 6, and that's it. So this term, discriminant, fxx times fy, so 2y plus 2 times 2, subtract 2x minus 6 squared. Now you could expand, but generally speaking, I encourage people not to. I think that you don't really gain anything by it. And oftentimes, you'll see a lot of things are very, very similar in terms of how the computation gets carried out, whereas if you expand it, you lose that information. We don't want to lose information. We want to gain information, right? That's our goal. We want to get as much information as we can. So now we plug in our 3 points. So plug in the point 3, comma 1. Okay, so everywhere where I see a x, I put a 3. Where I see a y, I put a 1. Okay, so that would be 2 plus 2, which is 4, times 2, subtract 6 minus 6 is 0 squared. Okay, well that's 8 minus 0. Aha, positive, great. But we're not done. What do we need to do? Well, what we need to do is look at our fxx and our fyy and see about what are they. Well, they're both positive because we have them right there. In fact, fyy, it's always positive. So the fact that d is positive, fyy is positive, we can put that together and say this 0.31, this is a local min. Good. All right. Well, how about 1 minus 1? Well, okay. So we put in negative 1 in for y. We're going to get 0. Well, that's not good for us. We put in 1 for x. We're going to get 2 minus 6. It's negative 4. And you square that, you get 16. Well, it's negative 16. But we don't really care about the 16ness of it. We care about the negativeness of it. So negative, saddle, done. How about this other point, 5 comma negative 1? Well, again, plug in negative 1 for y. Negative 2 plus 2, 0. See, as soon as this first term is 0 or negative, forget it. Can't be a min or a max. All right. Or if it is, it's only through hard work that you get there. Minus, okay, 10 minus 6 is 4 squared, 16, negative 16, still less than 0. So that means both of these points, these are both saddle points. So we end up with 1 local min, 2 saddles. And there we go. There we go. Good. Well, I think we have time for one more problem. One more to finish us up. You work for a company which produces Yops and Zons. Now currently, Yops sell for $3 each and Zons sell for $9. Oh, we should make a lot of Zons. Now the cost to produce Y Yops and Z Zons is 10 plus a half y squared plus a third z cubed minus yz dollars. Determine how many Yops and Zons respectively should be made in order to maximize profit. All right, good. Well, let's take a look. Okay, so let's think about it. There's a lot of stuff going on in this problem. First off, Yops and Zons. You're thinking, I don't know what a Yop looks like or what a Zon is. And it's like, okay, we don't need to. Really what we can do is we can say, let's take this problem and let's abstract it. That's one of the things that we're doing in mathematics, is learning to take a problem and translating it into our abstract tools and language that we have the ability to manipulate and work and solve. So we don't need to worry what they are. We just say, look, they are what they are. Now, you might say, well, where do these words come from? It kind of sounds like a Dr. Seuss kind of word. Well, it's because it's a Dr. Seuss kind of word. They come from Dr. Seuss books. So I guess if you really want to do some research, you can find out. So, all right. So anyways, once we can get past that, we're like, all right, fine. What are we trying to do? Well, we see that there's some sort of optimization going on, and we want to maximize our profit. Okay, so we need to figure out our profit function. Now you might be thinking, hey, profit, whoop, there's not x's, it's y's. Profit, that's not so bad. Don't they give it to us? Be careful. Make sure you understand what's being given, because it doesn't say that profit is this expression. What does this correspond to? It's the cost. Now you might say, how do we know it's the cost? Well, because it tells us the cost is the bar. Okay, so that's cost. Well, what's the difference between profit and cost? Well, the difference is for one thing, cost is how much you take out. Profit is how much you get to take home. So there's one other key factor, which is our P, which is, we're thinking of that as profit. Well, that's our revenue minus cost. Wow, I feel like I'm teaching economics here. So in other words, you say, how much did I get in from my sales? How much do I have to pay to make it? The difference between the two, that's how much I get to take home. And that's my profit. All right. So the cost, that's given. Okay, phew, good. What's the revenue? Well, the revenue is based off of what we sell. And we know we have prices. See, they kind of hid things on us by using words. Those sneaky people. They wrote the word 3 and the word 9. So that we may not see it the first time. But we saw it, right? Okay, so our yops are $3. So that means for every yop we sell, we get 3. So we could say, look, our revenue is 3y, and our zons are $9. So we'll get 9z. So that's our revenue. Now subtract the cost. 10 plus a half y squared plus a third z cubed minus yz. They might think, does that make sense to have a minus yz? Well, in some sense, this is an economy of scope. It's a very fancy way of saying if you do more, you gain efficiencies. So by having two simultaneous productions, you might be able to combine certain processes and thus be able to make it more efficient. So it is actually not unreasonable to have some sort of minus where you have a cross term going into play. And of course, the big thing is we see, look, our costs go up pretty dramatically in the long run. So in the long run, forget it, hopeless, or it's going to cost way too much because it's growing quadratically. If we're talking about our yops, it's growing cubically. If we're talking about our zon, forget it. Okay, so let's clean it up just a smidge. So we get 3y plus 9z minus 10 minus a half y squared minus a third z cubed plus yz. And I did something really important here. I think you saw it, and that is the parentheses, right? Parentheses are our friends, and in particular, the minus sign distributes through to each term. So make sure that when you're doing these problems, that you correctly distribute things like minuses all the way through. Okay, so there's our profit, and we're after optimizing. So we say, hey, we know how to optimize. Now we're going to look for where does our gradient equal 0. Okay, great. So we're going to look at our p sub y, and we have 3, okay, minus y, great, plus z equals 0. And our p sub z, well, that'd be 9 minus z squared plus y equals 0. All right, now, unfortunately, that z squared means that we're not linear, so we're not going to be like, ooh, fun combinations, and it all comes out, yay. Well, we can still do some combinations, right? So, for instance, notice that there's both of these have y's in them. Okay, so why don't we just add, right? What would happen if we added? We'd get 12. Minus y plus y would cancel. There's a minus z squared and a plus z. Oh, okay. Well, if we move everything across, that says z squared minus z minus 12 equals 0. All right. Well, now let's factor. We need two things that multiply to negative 12, but add to negative 1. I think we can do that. Minus 4 plus 3. Great. So, seems to be leading us to two possibilities. Z equals 4, or z equals negative 3. Now, I think we can rule out the negative 3 because you cannot produce negative quantities of items, right? It's not like you can say, okay, well, I'm going to go to my competitors and I'm going to just start destroying their goods. Ha ha ha. No. Calculus people would never do that. That sounds evil. And we know that calculus is to be used only for good. Okay, so we can say, look, negative 3 does not fit with what's possible. Okay, well, that says z equals 4. Now, if we know what z is, we can substitute. For instance, here, what can we say? Well, if z equals 4, that tells us that we get y equals z plus 3, or y equals 7. Okay, so it appears, and since we only have one viable option, it must be right, so we should make 4 of your zons and 7 of the yops. Okay, so there we go. There's the answer. But let's step back and say, we should check a couple of things. How do we know that we've maximized? It's actually a great question. And it's not so clear that we've actually succeeded in maximizing our profit. What's our concern? Well, we may have just minimized. We may have found the smallest profit that we can get. That would be terrible. A really poor way to run a business. So, what can we do? Well, what we can do is probe a little bit. Let's figure out and let's classify this. We can do that. So if we look at our PYY, PZZ minus PYZ quantity squared. It doesn't matter that we're not using X and Y. We can use Y and Z. That's perfectly fine. Okay, so let's do this. Where we have PYY is minus 1. That's pretty promising. PZZ is minus 2Z, really promising. And PYZ is 1. So when we plug in Z is negative 4 and Y equals 7, well, what do we see? Well, we're going to get minus 1 times minus 8 minus 1, which is 7, which is positive. So this is at the point 7, 4. We see, hey, positive quantity. It is a local min or max, but more importantly, when we look at these quantities, we say, they're negative. So indeed, this is a local max. Good. Phew. So now we know we're maximizing profit. So we feel pretty good. I will say that there's still one more concern. Now, as far as the problem goes, it's not a concern. And the question is, should we still make any product at all? Well, what do I mean? You might be maximizing profit and still lose money. It could be the case that says, look, even in the best case scenario, I lose money. And if you lose money, forget it. You shouldn't make anything. You should find a different business. So even maximizing profit doesn't mean that, hey, this is a great business model. So what can we do? Well, so if it were the question, should you produce? The last step would be, let's actually talk about how much money is being made. So if you wanted to make a decision about whether or not to produce, you would say, well, what happens if you plug these quantities in? For example, if you plug in Y equals 7 and Z equals 4, well, it looks like your revenue would be some number. 21 plus 36, that's 57. On the other hand, if you go through and run the data here, you get 10, a half of 49. We'll say that's 25. That's what, 35. A third of 7 cubed. Well, 7 cubed is a big number. it's 343. A third of that is about, what, 110? So, that's not looking promising. But then we're going to subtract 28. And so, well, you have to run the numbers out. Oh, whoops. I swapped the... no, it's not 7 cubed, it's 4 cubed. I can do math sometimes. 4 cubed, 64 times a third, that's 21. So we're up to like 46. We subtract 28, that's 18. Yeah. We should make. We're good to go. We're going to make a profit. Okay. Phew. All right. Well, that's it. That was our last problem for now. But of course, there's always more. There's always more to do and more to learn and more to practice. So I hope to see you again. Bye.